Good morning, everyone. Sorry for the delay. Right. So let's start with the color image processing. What we have seen last time. Just wait a minute. When you have problems that will arrive from anywhere, anyways. Yeah. So what we have seen is all about the color image processing, right? That what are the actual motivation to use the color image processing, right? One of the motivation because object recognition would be better because description whatever you are giving with the color that will help more. Just like I have given you the example of that cauliflower and the broccoli, right? To identify by just the shape, they both are very similar. So how you will actually describe that object? So if the color would be there, then it will be more, the helpful thing. Okay. So the human eye can actually see thousands of color shades, right? So to use that, we are doing this. The two major areas, that is one is the full color, another one is the pseudo color. Full color means we are using all the shades. So that what we are using into that DG cameras, and that time was there. Now here the technology is even more advanced than that, right? But in the cameras, in the TV, everywhere we are using this because they are using a full color model, right? So each and every color would be visible. Do you remember that when we were having the color TVs, initially it was able to show you only few colors. So they were not using this full model, obviously. But nowadays, the thing is different, right? And the pseudo color means they are having just a few colors. Range of intensities would be there. Then from this to this, if there would be red color or the pink color, it will be having fixed colors like 8 red colors, then light, dark, whatever it is. Same way for the pink. It is not like that they are having 256 different shades only in red color, then only in pink, then only in green, and so on. Right? That is what is pseudo color. Then we have seen about the color spectrum. This is what you have seen, right? The color spectrum, we know already if white light would be there, it will create the 6 broad regions, right? 6 different colors. And generally the human can see in ultraviolet band or in visible spectrum or in infrared. That is what I'm asking. Human can see the colors in which spectrum? Visible spectrum only, right? In ultraviolet or in infrared, we cannot see. Okay. Then this is what we have seen. If the light is achromatic means void of color, then the attribute is only intensity, or you can say the amount, right? Only intensity. That what we have seen, no, our grayscale image. Whatever the intensity is there, whenever we are reading the image, whatever values we are getting, those all values are nothing but just intensity of that color, right? If it is 0, then it is known as black color. If it is 255, then it would be white color, right? And so on. If there is a chromatic light, then it spans the electromagnetic spectrum from approximately 400 to 700 nm. So approximately from 400 to 700, the lights would be visible in the spectrum. Visible light is what? Relatively narrow band of frequencies in the electromagnetic energy spectrum, right? Those are just frequencies, nothing else. The color perception, how the human can perceive the colors on the particular wavelength only, right? Just like here you can see red color would be after 650 or 675 around, right? So from 700 to 750 it is more visible, right? This is for the blue color. Actually this is nothing but the wavelength in nanometer it is given, right? Then this is what we have seen, right? If the sunlight is there onto the object, then a particular wavelength, whatever the color it is, that color only it will reflect. All the other colors, wavelengths, it will absorb. So whatever is absorbed, that we cannot see. Whatever is reflected, that the human can see, right? So if this is what red object, then whenever the sunlight would be there on it, it will absorb the other colors, but it will only reflect the red. So human can see, okay, this is the red color object. Same way for green, same way for blue, right? Whatever the color is there, that will only be reflected, right? So color can only exist when the three components are present: viewer, object, and light. When the white light hits an object, it selectively blocks some colors and reflects the others. Only the reflected colors can contribute to the viewer's perception. So whatever the reflected color is there, that only viewer can see. Achromatic light. From here it is, I think, remaining one. Okay. So what is achromatic light? Its only attribute is its intensity, or whatever the amount, that what we have discussed, because it is not having any colors. So we are not actually discussing anything about this, because whatever we have seen, that is all about the achromatic light. Viewers can see only a black and white television set. That is what the example of this achromatic light. The term gray level, that refers to a scalar measures of intensity that range from black to gray and finally to white. So 0 to then 1, 2, 3, 4, 5, 6, whatever you are taking, that would be much dark gray colored, then lighter, 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 and finally you are at the white color. Right? What is chromatic light? That is what our interest into this unit. The electromagnetic energy spectrum from approximately 400 to 700 nanometer. I'll check my connection. Yes. Yes. Okay. So radiance. Radiance is what? Here we will be having three definitions. This is what we have seen into our first unit, if you remember. Radiance, luminance, and the brightness. For the brightness, we have said that it could not be measured anywhere in any terms, right? Because brightness is totally subjective. Person to person, it will vary, right? But radiance and luminance, that we can measure in watt and Lm, lumens, that is respectively. So what is radiance? The total amount of energy that flow from the light source, that is known as radiance. So what you can see from this light source, whatever the energy is there, this is known as radiance. That is on the object. That is a full energy. Now, what is luminance? Luminance is a measure of amount of energy an observer perceives from the light source. So that is very simple, that observer cannot perceive the whole energy. It's just taking a part of that energy, because it will be reflected somewhere onto the object. And whenever it is reflected from the object, it will only reflect that color. It will absorb all the other lights. So that is what known as luminance. So this would be luminance. This, because observer means viewer can only perceive that amount of source. That is luminance. But this is what known as radiance. Radiance, luminance. Right? Or you can see even this, right? But only viewer can perceive how much. That depends. So this is what about the radiance and luminance. But what is brightness? Brightness is what? A subjective descriptor that is impossible to measure. The achromatic notion of intensity, you can say, one of the key factor in describing the color sensation, right? You are usually we are speaking that you bought a very bright color shirt, bright color this, bright color that. So what is bright? That is subjective, right? You are feeling that that color is bright. I'm not feeling that's bright, right? So that is what we are using in the color sensation. That is what the bright color. Bright means very dark. I mean, if there would be here the pink color, bright pink. Bright pink means with the full intensity, right? So this is what brightness is very similar to intensity now. Brightness is very similar to intensity, high intensity, right? Low intensity, baby pink, light pink. So that's lower intensity. Higher intensity means it's very dark color. I hope you guys are getting what I'm saying is. Yes or no? Yeah. Okay. And you can just remember and I can next. Okay. Now this is what the color fundamentals. Absorption of light by the red, green, and blue cones in the human eye as the function of wavelength. This is what they have done experiment, right? Red light is there, green light is there, blue light is there. Now, what kind of absorption is there at the viewer side? Viewer can see those colors at which wavelength. That is what the experiment. Okay, so that is said to be that at 445 nm almost blue color is activated into your icons. There are more than 700 million cones are there into your eye, which are sensitive to the light, obviously, right? So which color you can easily capture? Can you tell me this? Which color you can easily capture? Where your eyes are actually much sensitive on which color? Red, correct. Very nice, right? Red color is much sensitive to your eyes. So that is why wherever there is any kind of danger or that sign would be there, that would be always with the red color. For choosing this color, reason behind that is this, right? Because your eyes are very sensitive to those colors. At 535 almost this one, and at 575 to 700, I mean your eyes are sensitive from 450 wavelength to around 700 for the red color. This is totally opposite to whatever the numbers they have given actually as the standard would be there. So CIE, that is what the standard, and according to that standard they are saying that for red color, it should be wavelength should be 700 nm. For the green color, it should be 546. For the blue color, it should be like this. But that is totally opposite into the original practical experiment. So before experiment, they have done their experiment, and based on that, they have given this. So there would be the mismatch over there, right? So approximately 66% of the cones are sensitive to red light, 33% for green light, and only 6% for the blue light. That is why for the signals also we are using red and green. The reason behind this is this. Absorption curves for the different cones that have been determined experimentally, and strangely this do not match with the CIE standards, right? It's not matching. These light standards were developed before the experiments, that is why. Then what are the primary colors and what are the secondary colors? The primary colors are red, green, and blue, that we know. And after mixing those, we will get the secondary colors also, right? So here the CIE specific wavelength values to the primary colors are this, that what we have discussed just. No mean that these colors are fixed RGB components acting alone can generate all the spectrum colors. No, not alone. You have to mix, you have to combine, then it will generate secondary colors. So what are the secondary colors of the light? They are cyan, magenta, and yellow. cyan color you will get after adding G and B, green and blue. Same way, yellow you will get after red and green, and magenta, red and blue. So this is how you will get the color. So mixing these three primaries or a secondaries with opposite primary colors in the right intensity produce white color. That will produce white color. You can see over here. These are your red, green, and blue color, right? And if you will add them with the right intensity, it will create the white color even, white light, right? And if you are adding this red and green, that would be more visible over here, maybe, right? You can see this red and green, it will create yellow. Green and blue, that will create sand. Red and blue, that will create magenta, right? And with the right intensity, they will create white color. But if here you have used the manner additive manner, if you will use here subtractive manner, then subtraction of from this secondary color to the primary color with the right intensity, that will give you the black color. So here you have used, this are your main secondary colors, cyan, magenta and yellow. Then if you will subtract that cyan plus magenta, it will give you blue color and so on. And at the right intensity, it will give you the black color. This subtractive manner and all, they are using actually into that Xerox machine, if you know. Xerox machine, whatever the color you are having, you will get over there the printout that is with the black or white color, right? So they are using the same funda over there. Okay. Again, back to this. In the right intensity, that will produce white color. Now, if primary colors of the pigments or the colorants, here what do you mean by the pigments? The smallest element, right? That is what the pigment. So here if you are keeping it as a cyan, magenta and yellow, a primary color of the pigment is defined as one that subtract or absorb a primary color of the light and reflect or transmit the other two. So it will be having that subtractive manner, cyan and that you can say the magenta color. If they will be subtracted, then it will create blue color and so on, right? Like that. So secondary colors of the pigments or the colorant, you will have this red, green and blue after subtraction, and the combination of these three pigment primaries or a secondary with its opposite primary, that produce the black color. So that is why we are having here black color. The same figure is there. So actually what your f of x is, this is what again we are on the first unit. Your f of x equals to I of x into R of x. So what is your I? Illumination, R for reflectance. If you have this two, it means that is your image, right? That is what your image formation model, if you remember. Okay. So here you have one color where your red is on, blue is on. So when your red and blue is on, you are getting magenta color over here, right? Because green color won't be there. So red plus blue, it will give you that magenta color. Yellow will be created how? Red plus green. So red and green, they both are on, blue is off. Same way, pure red color, only red will be there, green and blue will be off. Same way for green, red off, only green on, blue off. They are the pure colors, right? So same way you can draw for all the colors. So if the light would be there, right, all the other colors that will be, some of the colors would be absorbed, some of the color will be reflected. Whatever is the reflected one, that only the eye can see. Eyes can see. Okay. So till this everything is clear, say yes or no. Am I audible to you guys? Yeah. Okay. Okay. Fine. Great. Okay. Then the characteristics of color, because we are talking about the chromatic lights now. not about the achromatic. If there would be achromatic, only intensity will be there. But if this is the chromatic, then there would be the three main things. One is brightness, one is hue, and one is saturation. Hue means your pure color. Saturation means your red color with actually perspective of the white color. If you are combining into your pure color some white color, then whatever is generated, that is known as saturation. Few of the colors are there, they are actually the saturation free, like the pink color, and one more is there, violet maybe. They two are the saturation free colors. Otherwise, whatever the colors are there, if you will add white color into it, then it will generate another color, right? That is what the saturation, that will show the purity of your original color. So what is brightness? That is what the chromatic notion of intensity. So again I said, no, what intensity is actually your brightness into the color image processing. Then what is hue? Hue and saturation, an attribute associated with the dominant wavelength in a mixture of light waves, representing dominant color as perceived by an observer. Okay, so that is what the hue, dominant of a single color, you can say. Either it is red or green or blue or violet or whatever the color is, that is hue colors. Then what is saturation? Saturation means referring to relative purity or the amount of white mixed with hue. So suppose hue color is your pure red color. In red color, if some intensity of amount I am adding of that white color, that is what my saturation, right? So white with red color. So saturation is inversely proportional to the amount of white color. That is very obvious. Whatever the with intensity you will add the white color. You have used that, no, in your schooling days, that colors, right? The watercolors. So how you are making the combination? If you want the sky blue color, what you will do? You will take a pure blue color. In that you will add white color. But in what intensity you are adding, according to that it will give you the sky color, right? Dark or light. Simple, right? So hue and saturation, that is taken together, because we cannot separate it out actually. So if we are taking that consideration in a single unit, that is known as chromaticity, right? So hue and saturation taken together are called chromaticity. And a color that may be characterized by its brightness and chromaticity in color image processing. Not only intensity, just like your achromatic, where you were not having any colors, you were only using intensity, right? But in chromatic, in color image processing, you are considering both the terms, brightness and chromaticity. And actually three terms, because brightness plus this chromaticity means hue and saturation, both you are considering into a single unit, right? So it means in the characteristics of colors, you are concerned about brightness, hue, and saturation. That's it, right? Then what is the purpose of color model? Because now we are going on to, we are moving on to a very first topic of our syllabus, because our syllabus gets starts from color models. So this, whatever we have discussed, that will be useful into your color models and the pseudo colors and all, right? But you should know what is chromaticity, what is that, you know one of the spectrum, electromagnetic spectrum, how the colors are visible into it, what should be the wavelength, what should be reflectance, right? And all these things. Okay. So what will be there in the color models? The purpose of the color model is to facilitate the specification of colors in some standard. Color models are oriented either towards the hardware or applications, because whatever the color model are actually suitable, that will be used in that particular hardware. You have again, heard somewhere RGB color model, CMYI model, CMYK model, CMYK models and all, they are using into the one of the printer, right? So those kind of color models are there, which are present, which are actually based on either whatever application you are using or whatever the hardware you are using. Suppose if it is the hardware oriented, you can see that in color monitor or in video camera, you are using RGB model, because RGB is actually providing the full colors, full color model, right? All the color intensity would be there. If you will say about the red color, no, for red color also you have 65,000 shades. Just imagine, right? So in that way, then the color printer, what they are using CMY or CMYK model. If it is your color TV broadcast, then they are using YIQ model. That is not in our syllabus, but I have just mentioned this thing into the one of the application, right? YIQ we are not going to see. Then the color image manipulation, because you want to again manipulate some of the things into the color image, also you want to do the manipulation, then HSI or HSV model will be used. Use saturation intensity. In image processing, you are using this RGB or YIQ or HSI model whenever you want to do one of the processing on your image. That is what the image processing, whatever you are doing. Right. So next time we'll start with this RGB color model. Right. Already late because of me. Fine. Okay, fine. So you can write down your numbers in any order you wish. Fine. You can write your numbers here and you may leave. Anyone else who still remain to write the numbers, please write it down. Akash, Hinal, Kabir, Prince, Shivanand, Viraj. Akash, Hinal, Kabir, you can write your enrollment numbers and you may leave.